8 and 7, I introduced the idea of two possible different products that actually ended up being a lot more than just two possible products that can be produced from an elimination reaction. So because an elimination reaction attacks a hydrogen at the beta position, if there are multiple beta positions and multiple hydrogens at the beta positions, there's a possibility of multiple different products. Which products you get, I alluded to, can be determined by the base that you use. So let's remind ourselves, if we have a substrate and we have a leaving group, the little red dot is our alpha site. If something attacks the alpha site, it's a nucleophile. So nucleophiles attack at the alpha site. But the same thing, just called something different, called a base, can attack at the beta site. Since this is the alpha site, this is the beta site, this is also a beta site. A beta site is one away from where that alpha site is located. So a base will take a hydrogen from a beta site and push electrons towards the alpha site, which cause the leaving group to leave. The question is, since there are so many different hydrogens that are in a beta site, how could we design an experiment such that the base would choose some hydrogens over another hydrogen? So let's see if we can figure it out. If we chose one of the blue hydrogens, then what would happen is the base would come, it would take a blue hydrogen, it would push these electrons towards the alpha site, and it would cause the leaving group to leave. And that would create the following compound. It looks like I'm missing a methyl group right here. It would form the following compound. We know, because that compound is the one that has a double bond in a less substituted position, that that product would be known as the Hofman product. On the other hand, that base could also attack a different hydrogen or a different beta site. If it attacked this hydrogen, it could push these electrons in, forcing the leaving group to leave. So the orange arrows are one mechanism, the blue arrows are a different mechanism. It's not happening at the same time. And that would create an orange double bond of this substrate. And this substrate is more substituted, so we would refer to as that double bond as being the Zaitzev double bond. Now, what's going to happen in general? In general, if we just use a regular low mil type of base, I'm going to get a mixture of both the Hofman and the Zaitzev. In fact, I know that Zaitzev is going to be the better product because Zaitzev is going to be the more stable product. I do, however, have a little bit of an inkling. I know that if I design my base in a certain way, I might be able to choose one product over another. How could I choose one over another? So let's think as if we were the molecules. If you were the molecules and you needed to specifically choose the hydrogen that was orange, what kind of characteristics might you have? Notice that the hydrogen that is orange is more secluded. He's more isolated. If you actually look at the bond length of a hydrogen, it's actually pretty close to where the carbon is located. So these methyl groups are kind of in the way, as is the other structure here. It all has free rotation at the same time. So this base has to go into a very narrow position and steal a hydrogen while not getting hit by everything else. This is like a helicopter. If it hits you, you're out of there. So what kind of base would I choose if I wanted a base to take the hydrogen from a very tight space? Well, think about it. If you're going to steal something from a bank and you're doing a bank robbery and you need an individual that's going to fit through the air pipes, you're not going to choose a 300-pound person because they're not going to make it through the air pipes. You're going to choose a really small person that can fit through the air pipes and make it inside to be stealth-like and steal hydrogen from inside the bank. On the other hand, if you wanted a base that was going to steal the hydrogens here exclusively, those hydrogens are much more available. They're much more accessible. They're outside, they're free floating. All this other stuff is not coming in the way of those hydrogens. So if I wanted to make sure that my base took one of those hydrogens instead of taking this hydrogen, I would make sure that my base could not take that hydrogen by choosing a very, very large base. So as it turns out, we can design an experiment such that we can produce the Hofman as the major product, or we can produce the Zaitzev as the major product. Their stability is not in question. The Zaitzev is more stable and will always be more stable than the Hofman. But what if you just couldn't produce the Zaitzev product? What if you were going to steal a bank and you didn't have a little stealthy person that could go into that hole? You only had this mammoth 600-pound person. Well then, if they're that big, maybe they could just like knock in the front door because they're that big. So the size of our base can help us to predict which product we're going to get, whether we're going to get the Zaitzev or get the Hofman. There are many different products in your book that show you very, very large bases. Some of those bases include OT-butyl, or potassium O-tert-butoxide. Another one that is shown in your textbook is potassium or lithium or sodium tert ethoxide. Also very large bases, DBU and DBN. There are a couple of more that are shown in your textbook, so I recommend going to your textbook and just memorizing a couple of these very large sterically hindered bases. I'm not even going to draw what DBU and DBN look like, but in the book, when they show you the pictures, you're going to see that they have something in common. They are very, very large. The way that I remember it is the B is really big. And so whenever I see these acronyms, I just focus on the B and I remember that these are really, really big bases. So these bases are going to prefer to take the hydrogens that are more available. And anytime that I use these bases, I'm going to get the Hofman as the major product. What kind of bases would predominantly give me the more stable product? Well, anything that was small and slim and could get into that little hole in order to remove that hydrogen. Remember, it wants to produce a product that is more stable. If the reaction is reversible, it's going to go back and forth until it reaches the more stable, because that's what equilibrium does. So I would want to focus on something that was streamlined, something that was strong. What kind of bases are streamlined and strong? Well, the classic one is an OH. You can't get much smaller than that. But other ones, OET, hydride, these are always really small and specific bases that are going to remove a hydrogen from a very tight place. So these compounds are going to produce the Zaitzev product as the major, because these bases are streamlined. These bases are what we refer to as bulky or sterically hindered. Steric hindrance is the organic name for anything that is super really big. So I can't choose just one product. It's not going to happen. Nature just has a way. Sometimes even that 300-pound person can find that hydrogen. He just came out of the bathroom at the wrong time and there he was. So I can change the percentage of my products, but I will always get two products. So whenever I have a substrate that can eliminate to form multiple double bonds, it will produce multiple double bonds. It's just that depending on the base that I choose, I can choose a major product as being the Hofman product, or I can choose the major product as being a Zaitzev product. So this, in order, allows you to choose between those two different products by using a very well-designed base. Both of these require strong bases in order to be able to pull off an acidic proton, or a proton that is beta to the alpha site.